Hello, in this video I will introduce you to the white chalk optimizer algorithm implemented in Python. Additionally, I will demonstrate its performance on 3 tasks from CEC17 and 1 practical real-life problem. You can find the complete source code in my GitHub repository, linked in the description. The link to the original paper on this algorithm is also provided there. Let's get started. The code structure can be divided into 3 parts: the white chalk model, which stores the values of its coordinates and velocity; the optimizer, which performs the necessary operations for the optimization task; and the main function, where data preparation, boundary setup, and fitness function creation are carried out. This code defines a Python class called whitechalk that models an entity with a velocity, position, and a defined search space. Here's a narrative explanation of its functionality. First, we initialize our whitechalk object. The init method initializes a whitechalk object with 3 attributes: velocity, a scalar value representing the chalk speed; position, a list of floating point numbers representing the chalk's current coordinates; and a multidimensional space; and a search space, a list of tuples where each tuple defines the lower and upper bounds for the corresponding dimensions of the chalk's movement. Then we have position adjustment logic. The adjust position method ensures that the chalk's position remains within the boundaries defined by its search space. If a certain coordinate is outside the limits, then it becomes equal to the nearest value of the minimum or maximum boundary. Here the optimizer is initialized, where the fitness function, the population size of white chalks, the condition for the fitness function, whether we are looking for its minimum or maximum, the maximum number of iterations, and other parameters necessary for the algorithm's operation are passed. These parameters are described in more detail in the paper. Further code can be divided into 2 main parts. First, methods that change the parameters of the chalk, and second, methods that provide the necessary information for the first group, which changes as the algorithm runs. Here's the first group. In the initialize population method, the chalk swarm is created based on the previously set parameters. The update velocity method updates the chalk's velocities. This is the position update method, replicating formula 10 from the paper. And another one corresponds to formula 16. Here's next part. We reach the second group of methods, which, so to speak, serve the first group. These are new P1, P2 getters. These are MV, W0, A coefficient getters. Here are WSO, K, P1, and chalk predistance getters. And finally, here are the methods that directly link the above-mentioned methods and perform the optimization. Evaluate population method evaluates all chalks in the population to determine their fitness, identifies the best performing chalk, and updates the global best fitness and position. The optimize method encapsulates the entire optimization process. It initializes the swarm and evaluates the initial fitness. It iteratively updates the velocity, position, and boundary constraints for all chalks, evaluates the fitness at each step to track progress, and identify the global best solution, returns the best solution and its corresponding fitness value at the end of the process. Now let's look at the application of the algorithm on test cases. First, we'll consider the tests conducted by the authors of the paper for their algorithm, specifically the CEC17 functions 3, 9, and 13. Here you can see the test results for function f3. As we can observe, the Python implementation successfully found the correct result. However, compared to the author's results, the test differs in terms of average, worst, and STD parameters. It's quite intriguing how they managed to achieve ideal results on their first try, judging by the results. Next, we have the test measurements for function F9. The situation is largely similar to the F3 function tests. Finally, for function F13, we can see the implementation didn't arrive at the final correct answer, but it got very close to it. However, based on the results, we can also observe that the algorithm started searching in the right direction much earlier than it did in the author's results. In addition to the standard optimization algorithm tests, a real-life test was also conducted. One of these involved determining the minimum required material for a cylindrical can, which must have a volume of 1.5 liters. Applying our algorithm to this problem is quite straightforward. We just need to modify the fitness function that we will minimize. We'll have two variables, one for the radius and another for the height of the can. Additionally, if the volume of the can is less than the required value, we will penalize this case by assigning it an infinitely large positive value. And voila! We get the same results as the calculation using mathematical transformations. This example was taken from a video on the Professor Dave Explains channel. I will leave the link in the description. Thank you for your attention.